Good afternoon, gentle readers. It's January 14, 2025. 2025 is what year it is. And today, from a desk with Ross Finlayson here in Seattle, Washington, another installment of Logos 2000, 21st Century Foundations of Mathematics and Physics is the study here. And it's figured there's kind of a consideration of the continuous and the infinite as these super-classical notions that since all pre-antiquity have comprised the higher order of mathematics and have been found that implement the perfect analysis that's calculus and all such matters of reason and rationality and beyond the merely inductive to the fuller dialectic and the fuller deductive, the theory of the things. So today in Logos 2000 is not so much of an established course. I'm trying to figure out the balance on the camera and trying to convince it what the background is of the lights and this kind of thing. As with regards to very rudimentary video production and editing skills, say. I never really got too much into like a toaster apparatus or what's like on the Macintosh, say something like Final Cut Pro or anything like that, or vis-a-vis still understanding a bit about the contents of file formats and these kinds of things. As with regards to what is just part of the feuilleton or the contemporary usual things, if not so much about current events, which are not always good and sometimes are very troubling. So that then there can be, for somebody who studies mathematics and foundations, kind of a place to put their worries, because at least there's one good theory and then it deserves an ontological commitment, say, vis-a-vis trying to make sense of the world and these kinds of things. Not relevant here for this technical setting. And then that also, like, the joys of the world are super to that, but here it's just kind of a mellow, quiet talk about mathematical foundations and this kind of thing. So what I found was a great history of mathematics. So Boyer is this guy's name, and Carl Boyer is a mathematician and a historian, and he writes histories of mathematics. He wrote the development of the conceptual development of the calculus, and that's where I first learned about like the Mertonian school in Oxford, the Swinestead the calculator, whatever his name was, and Bradwardine, who wrote a book called De Continuo about the continuous, hundreds of years before Newton, and hundreds of years before Galileo. And so they were working on the analysis and the mathematics and the mechanics that arrived at much later Galileo and much later Newton. And so then also, of course, in the conceptual development of the calculus, it goes into the classical accounts of methods of exhaustion, what happens in the unbounded, what happens in the infinite. And so that's always after what's called the standard linear curriculum, where it's just given the definition of limit and some inductive and deductive accounts why it's so, and then whether or not it's really so or just not so, it's kind of left open, and then there's delta epsilonics, then after given some rules of the laws of arithmetic of real numbers and the comparison and contrast of values, or just the comparison of values, delta epsilonics, then getting back into when that's just after there's already developed like the whole coordinate setting and the Cartesian and the orthonormal vector basis, and as with regards to the polar coordinates and the formula or functions these days, the conceptual development of the calculus, the differential and integral calculus, is really pretty great. And much after I read that, as like MacLaurin's treatise on infinitesimal analysis, that's like the best formalism of the day. That's Newton's time, basically having that MacLaurin wrote this book called Infinitesimal Analysis, and then a hundred or so later years after that, then there was Weierstrass and Cauchy, and so then that's kind of how we have what's arrived at delta epsilonics, and that is like, here's a kit, and this is what we're calling it, and this kind of thing. That can also be read from MacLaurin, who I really admire, and whose style is from a time like 300 years ago that yet reads like very modern, which is surprising. So and then Boyer, he also wrote this book about the rainbow, the arc-en-ciel, the arc in the sky, vis-a-vis, the bow as like this ancient instrument of the bow and arrow, and it was related to other things in the sky survey, the stars in the sky, and especially about like the success of mathematics as a science of determining something that's according to optics and its super classical behavior of optics and light. And so what's really pretty remarkable about those kinds of things is the ways that light has diffraction and refraction and refringence after reflection, and the carriage of the image and the carriage of the intensity and the dual particle and wave nature of its theory about its elements and the particulate and the aggregate. The Carl Boyer's book on the rainbow is great because it helps explore the whole theory of light, and so it kind of starts in the ancient times, like the Norse theory of the rainbow, the Egyptians or the Sumerians' theory of the rainbow, and then it arrives at Descartes, who's because there had been attempts to figure out, it's like, well, why is this split like to so, and then people usually will associate light with like Newton or something like that. But it's really kind of this wider course about the optics and the lens makers and these kinds of things. A lot of that seemed to be centered in Denmark for some reason for quite a while. But then there's also like Milan or the Italian school of optics and this and that. So that's just kind of the course of the book. And then after Descartes, who is mostly known for philosophical stuff and then some matters of analysis, like the notion of the coordinates and these kinds of things, and all what can be. Descartes is very broad, but then also he's very fine and refined in implementing that some numerical methods that arrive at why the shape and the spectrum of the rainbow is like it is so. And then later it gets into like mostly Airy and Young. These being eventually like 18th century, 19th century, 1800s, the theory. And as if we read up to hear about like from Rude's modern chromatics and this kind of thing with regard to the dual tristimulus color space. And then even today, science has got kind of a halfway account of optics and light. And then they usually just kind of figured out both ways, but largely the whole theory in the story is just one way or the other. So that's just kind of its own thing. And so then this book, The History of Mathematics, is the second edition, which meant it actually printed and sold enough books that they printed some more, because it costs money to print a book. And then if people don't buy it, then it or read it, really, it just needs to be read, really, is the thing. But this book is a pretty great book, and so for somebody who studies mathematics and for studying foundations, you have to study the history of it, besides just having kind of like a linear curriculum or development of what's the foundations. All that's arrived at being able to relay it in the whole intersubjectivity and interobjectivity by the history of it for the future of it, what is the present of it. Then this book is actually really pretty great because it's just kind of solemn, yet it's like it's profound. And Boyer, he gets started and then he starts with the Egyptians. And so he doesn't really say much yet about, or having said much about the Atlanteans, or that kind of the pre-Noachic, he calls it, or before the flood, the antediluvian. The time's about 4000 BC, which used to be like, and is in some chronologies like the start of the world. And it's basically kind of, and then as we read from that one book about the fate of Atlantis or whatever, that it could have also been associated with the landmass in the Atlantic Ocean across from the Atlas Mountains called Atlantis, vis-a-vis that being in the middle of the Atlantic Ocean and actually connecting the Americas and the Europe and Africa thousands and thousands of years before, not actually connecting by a land bridge, but connecting by being navigable by boats on the sea. Boyer starts with the Egyptians and their arithmetic and their ideas about geometry, and the idea that they had some pretty good geometry, but it's not quite clear where it came from, because it didn't much change for a couple thousand years. But it was very successful and suitable to build like the pyramids and to help manage the floods of the Nile and all this kind of stuff. And he gets into like that those people then were called the rope stretchers, the surveyors, they were called, with regards to that being kind of the science of the study of the survey and the use of mathematics to quantify things. So that was kind of part and parcel of that part of the world. And is given as part of the history. And then I've only got about 15 pages into it, and then he gets into the Sumerians. And so he describes the Sumerians as being at least 4,000 years BC, before 0 AD, before Christ, before Common Era, BCE. And the Mesopotamian, what became the Chaldeans in this, and what later became, as he put it, it's called Mesopotamia, and they're the Mesopotamians. It's the cradle of civilization, as it were. The Fertile Crescent is related to this part of the world, and he helps explain why then that the Congress and the commerce in the world and conflict in the world went through there, and so up to the times of like Cyrus, and then after that about the Macedonians and Alexander, or over 3,000 years or so, arriving up to like 100 BC. Then the Sumerians developed positional notation to write in numbers, meaning instead of just like a different signs for larger and larger numbers, they just have like in a row, it grows according to orders of magnitude. So the positional notation for numbers. So we got some formulas, and that the Egyptians had these the means of the fractions, the continued fractions, because to them everything was kind of a unit fraction of sorts. So it was like 1/20th or 1/3, and so they really just figured out most things about it. It was like, what happens when you take off a third, and then we're able to get approximations. And as with regards to then their approximation for pi over 4 was like 1 minus 1/3 to a given power or something like that. That usually we think of like 22 over 7 is like one of these old approximations for 3.1415 and 926 ... pi, the transcendental number. But what I learned from reading this so far is the Egyptians kind of had it instead as like this numerical approximation, after an account of an approximation that is related to their systems of unit fractions. And then the continued fractions, which is a way of writing numbers as like this over that, over that, over that, over that, and then carrying it out, continued fractions. Then there's some of those that are the continued fractions, which make for like these Egyptian continued fractions. And so that's kind of how those were the objects of the theory or their arithmetic. And so that was just kind of a thing that I've been learning a little bit about from this history of mathematics. So this book was published in (1991), but it was copyrighted in 1968. So it was written in 1968, but the second edition may have seen some minor changes and updates. It's printed by John Wiley and Sons, Inc., out of New York, Chichester, Brisbane, Toronto, and Singapore. And it's revised by Uta C. Merzbach. the director of the LHM Institute. And Boyer dedicates it to his folks. And then there's a foreword by Isaac Asimov. Asimov was this really great author of the 60s, 70s, and 80s. And maybe before always, and maybe after a little bit. And so he's most familiar for his series in science fiction, like I, Robot, Foundation, and each one of those having like 5 or 6 or more books in their series. Those are series of books. And so Foundation is a pretty great story, and then the robot books are pretty great, and the Steel City and all this kind of stuff. And then Asimov has some other ones, and I'll be sorry that I'm not remembering them a little bit more directly right now. But Asimov has some other really great science fiction works. And the story about Foundation, like especially kind of like when it was trying to figure out what if the mule was going to like turn it over or something like that, that was pretty scary. I mean, but it turns out pretty well, you know. I mean, it's epic, you know. Then the robot books, and it's like, and the ideas of the development of the mental models of mechanical inference and questions about the human condition of a man's invention of a sort, and the emergence of these kinds of things, the exploration of that in and especially in text has a lot going on, and there's movies of it, but sometimes the movies can't really relate the concept. And yet at the same time, one hopes they're really good. Kind of like 2001 is like, it's incredibly dull the first couple times you watch it, but at some point in time it's like, and it's profound. One hopes, but that's a little bit more from the state of mind of you know, a great production, a great direction, and this kind of thing. Though the Asimov, he for writing this fiction, and it's very popular. Then there's this nonfiction, which is also incredibly popular, very widely distributed. And so he'd write up something like the genetic code or chemistry or something like that. And so in a little book kind of about like the size of this Lincoln Barnett's on Einstein or something like that, would be a good introduction to the theory of the gene, or the science of chemistry, and what are the elements and how they're organized and stuff like that. He introduces these concepts like the ekpyrotic and eka-lead and eka-mercury with regards to the isotopes, and the particular states of matter that aren't really part of the usual account, but are so. They're usually called exotic, or here with regards to eka-mercury and eka-lead, and things like matter and antimatter and these kinds of things, that while introducing the linear curriculum, Asimov also puts out all these other cool and interesting ideas. Asimov once got a prize. He came, like there was some challenge or something like that, and the National Laboratory was struggling with it, and so he sent him in the answer. So he got like he got a citation or something like that for that. So Asimov wrote this beginning here, and let's see what it says. What it says is it's in really glowing and benedictory terms about mathematics. Mathematics is a unique aspect of human thought. So here it's just kind of reason and rationality, or rationality and reason, and then mathematics kind of follows. There's logic is kind of how is the kernel of this, and so kind of like there's reason and rationality, and then there's logic and mathematics, and because it's part of these complementary duals and the completions, the meeting in the middle of nowhere, because either side, one way to the other, kind of reaches out towards the other, and inductively it'll never complete, but inductively it attains to the other one. And then it's whether deductively it completes, is the idea of the limit existing, and the limit being reached, being the true infinite limit, the true infinite and continuum limit of these things, vis-a-vis almost close enough. So when mathematics is unique, as Asimov puts it, it's kind of like it's unique, yet at the same time it's so multivarious that it's reflected in so many things. And then how it can be arrived at, there's exactly one of them. There's one universal objects to all the mathematics, is that anybody has their own theory of the mathematical objects, and whatever is true in their form, structure, and relation to those is what's true about them. So anybody else's is only so true to the others as they have, so the relations hold. And where they don't, they don't. And those are also the relations that establish themselves. That we always have the inner and the outer of these products, vis-a-vis the direct products and the sums of these things. So with that as a way of kind of looking at it, then when Asimov says that mathematics is special, it's just kind of like, it's like it stands up for itself, it provides a defense for itself, and provides a shelter in itself, kind of, because in matters of quantity and form, it always relates. And then sometimes it doesn't matter whether or not that does, because other things define what is or isn't proportion or form. But Asimov says that mathematics is cool. And then Asimov says his history is different. And then he talks about like changes since 25,000 years ago, about fashion and style, and what comes in and out of fashion, or style is like fashion goes in and out of style, but style's never out of fashion, or something like that. I forget what that is. But it's talking about here the science and the progress in the science. And so when we talk about the progress in the science, it's one thing to say that we have more of mathematics and it's good that way. But then when it's harder to tackle or understand, to set up a block and tackle and help to move things, to make it fungible and tractable, sometimes it takes these deconstructive accounts to arrive at the pieces back together after the fact of taking advantage of the great wealth of all the learning that went into making mathematics, the study of it today. And then how refined that's become. Here that's usually given an account of that, well, yeah, after real analysis, then there's a whole school and an industry of complex analysis up in the complex numbers. Because sometimes those don't apply, and besides, everyone's forgotten that they have a second branch of division that's ignored. So here it's like this deconstructive account has to include this original analysis. Then it's similar with his inner and outer products for the direct product, and then variously cross products, and the sums, or when things are brought together about how they meet and where they meet, and then how they met, or these kinds of things. They're points in their spaces. That there's developments that are one-sided, and that can be also considered the great development is kind of like it's one-sided in its own way. So trying to revisit what goes into the thinking process and the formalisms that arrive at that sometimes makes for this necessary to revisit these things and make a deconstructive account. The idea that the deconstructive account arrives at what are the elements again and what can be recomposed again. And here that's framed in terms of things like arithmetic and algebra for analysis about the objects of geometry and number theory, and that being about function theory, topology, and the operator calculus. That's the deconstructive account here. And even deconstructing arithmetic and deconstructing algebra and these kinds of things. To reconstruct them, or structuralists, everything comes back together and is a thing. That these sorts of approaches then are also like for energy and entelechy in this theory of physics. It's like, well, it's all equivalent. Well, yeah, but it's all different. And so trying to figure out these synthetic and integrative and deconstructive techniques to arrive back at the structuralist, the whole thing, is part of why the development is turned over variously. And so while Asimov is saying is like, we got big mathematics and big science, it's like, well, yeah, but that still is just through a lens, and these vary. So he says societies consider their own ways natural and rational, and find the ways of other societies to be odd, laughable, or repulsive. And so this is like the in-group, out-group kind of thing, but it also reflects kind of an idea that sometimes it's the opposite. So it varies. But this is kind of through Asimov's lens. Among most branches of science, the process of progress is one of both correction and extension. But then what he goes on to say is that but mathematics is perfect, so a mathematical proof is enduring. And so once a mathematical proof is established, then it's not something that ever needs to be fixed. And so so that's kind of why he says that the history of mathematics is different. And while that is so, that is so, and it's very much so that mathematical proofs are enduring and resistant to meddling in a sense. It is as well so that these deconstructive accounts make to afford that even very, very well understood and very well explored theories can just have another side to look them through and over. And if and where it's so to do so, then we also have this side history of all the attempts that were made along the way that would have been the other side, or would have been the fuller branch that were kind of left behind. And then it's whether they kind of grew along and became part of this river and this course, or just kind of trailed off and never quite developed. So with so much of the labor and the interest that goes into these things. So Asimov's account of history of mathematics as reflecting something that has never gone wrong, still doesn't have that some of the things haven't come in and out of style or fashion, or been understood to be later be incomplete or inconsistent. Where the only thing that can be wrong with something in mathematics is to be incomplete or inconsistent. It can be wrong how it's applied to anything else, practical matters. That's not mathematics' problem. It's only that it's just an issue in relating things. And so it is so, kind of as Asimov says, though, that mathematics, once it is established, is good for what it is. And it's not like other matters of philosophy or society that would later be wrong. I mean, once an object is in the universe of mathematics, it always is. It's enduring. It's eternal, even in a sense. That though all these material concepts of the societal and the historical, besides, and the interpersonal and these kinds of things, are their own milieu. And so that's part of what's called here the human condition, which is where we all live, and it's a nice place. And yet it also expresses all the range of the ethos and pathos and these kinds of things. So, and then he's talking about Aristotle. And Aristotle was wrong about his mechanics. And then he said Galileo corrected him, but then now we know we're like revisiting Galileo. You know, we have an account here from Moment in Motion that it is the world's turn bit, that have it so that there's not quite the same thing here for Asimov. So Asimov still himself here, when hopes would be kind of cracking a smile and say, "Yeah, you got me there, bud." And then he talks about Galen and Vesalius and Harvey hundreds of years later, about the theories and their developments and the dogma, and the dogma includes that dogma changes at some point. Yet the kind of resounding, enduring dogmas are kind of held up as good theories. And so here that's usually pointed at Euclid's geometry, and in these discussions here, for example, as after Derrida and Husserl that it is so that geometry is the numbers, and there's also the geometry is motion bit. So that's part of the theory here, and it's very dogmatic, and it's quite canonical. So that's just pretty usual. And he says, even Newton, the greatest of all scientists, is what Asimov calls Newton, was wrong. See, I wouldn't see Newton as the greatest of all scientists, except he's just kind of he's an idol of these things. And he says, now we can see what makes mathematics unique. Only in mathematics is there no significant correction, only extension. See, I don't agree with this, because we're constantly turning it over, and if there was ever anything that was wrong, then that would have to be, fixed or unextended. Because sometimes an extension is a growth. Another time, extension is an ingrowth. So it in either way can be sensible, fungible, and tractable and make mathematics. But one or the other way is either incomplete or inconsistent with respect to the other. These complementary duals, and the inner and the outer, are always present. The inversion here, not the contradiction, is the idea. That in this philosophy of mathematics, it is so that then all that later would be part of a wider, fuller milieu and a dialectic, and become altogether one thing, and in an altogether intersubjective, equity interpretable with another model language. Yet it does reflect upon that Asimov's idea is that mathematics is enduring, and it's worth an ontological commitment. The part of somebody gives in their beliefs to something is like, I can believe that. It doesn't offend my sensibilities or make something that's impossible to believe mathematics vis-a-vis other matters of fact and belief, like hope and these kinds of things, which sometimes by their very nature are the voluntary submission to ontological commitment. And then that, whether that's combined with that, and part of that notion is that it's built in or it's innate in this kind of, in the spirit of these things, vis-a-vis that mathematics is available for a very strong technical ontological commitment, and it's insofar as it's not just accepted a piece or a picture of it, but actually kind of the thorough account of it. Then that way it's to be separated theories of mathematics that are scientific and merely logicist and positivist, and their applications to what's the fallibilist, nominalist, and fictionalist, which are safety realms to say is like, I was talking about a theory, but it's not right, so don't blame me. Because then there's a real theory. The reason that mathematics objects have this strength is that there's a real universe of mathematical objects, so it's true. And then it's the theory of truth, and that's addressed in a lot of these talks with regards to the fundamental question of metaphysics and why there's a strong mathematical Platonism to make for us a stronger logicist positivism about the universe of mathematical objects and the technical. So so mathematics grows then. It says Euclid was incomplete, and then he's talking about, and there's various cases for matters of perspective and projection, out of scale, not to scale, off the map. Then there's various kinds of ways to look at what the consequences of otherwise the postulates of geometry would be. Is it not Euclidean? Well, if it's continuous, it's kind of Euclidean, because at some point, and this idea of the Poincare completion, the continuity, about the theory of manifolds that was discussed in the continuous manifolds a few episodes ago, because that's also about like how the space-time is flat and reflects that the universe is continuous. Asimov is quite enthused about some of these other approaches, which make for abstractions and extra bookkeeping dimensions that are yet free of what their attachments may be, like the complex analysis and various notions of higher dimensional space, say, which has just got a free scratch pad in the space unless it's established. It's also all continuous and contiguous too. This energy and entelechy, the contents and the connectedness of the things. That otherwise, he does say, yes, the Euclid's theorems are still valid to this day. That's something I'll be looking at. I'll be trying to figure out something like, well, what's one of these theorems where it's like one of the other postulates, come to play. But mostly that would ruin the entire notion of the metric of the norm and the affine. But it's kind of like the point of torsion, or the central moment. And as with regards to why when people talk about Euclid's geometry and non-Euclidean geometry, that is super-Euclidean geometry is the usual idea. And then with that, it's only that parallel lines might meet at infinity. And then as with regards to also something like there's an angle that is open or something like that. That otherwise all angles are on one side or the other. They're not aligned. That an open angle here is just a straight line. That two things that are perpendicular open in dimension inside. That this goes with this original analysis, what's called the identity dimension, kind of. So I'm just kind of having this idea, trying to look at super-Euclidean geometry as kind of this sub-Euclidean geometry about angle, and then it's kind of Cartesian in a sense. And the idea is that we think of an angle, and it's a right angle, and so it's two lines join and make an angle, and it's a right angle. And so then everything within those is kind of like about the quadratic weave and the web of those. So what happens when you double that angle, and now it's just a straight line, and it's not even an angle anymore. It's just there was a point on the line. And so that's kind of the idea of this identity dimension bit is like, well, you take a right angle, and what happens if you draw a line right through that? So now you got two angles in there that just split the right angle. And so when you open that outside, then they become right angles. So it's just going to show that there's ways to look at like lines that are parallel and never meet, and then angles that are fixed, and with regards to where those they would meet. The inversions of these. So I'm going to try and develop that as one of these new idea fixes about the after this Poincare completion bit, as we're talking about in the Euclidean and the sub-Euclidean, for this original analysis in this identity dimension. These are the ideas from this descriptive differential dynamics, a second course in differential analysis. Submersions, symmetries, and sheaves in this for the and the complex analysis in this identity dimension and original analysis. That the idea of this geometry then being inside and outside is, well, first we got this axionomist geometry, so Euclid's geometry just arises from it. We got a spiral space filling curve, and it gives a compass and an edge mathematically. And then as with regards to the Archimedean spiral, it's also kind of exists off that too. And so then this idea, though, of the deconstructive account Euclidean geometry is about this an open angle as a straight line, or the sub-Euclidean type thing. Something else to kind of further explore at a later date. So Asimov goes on to say, is like, now we can see what makes mathematics unique. And he says Euclid was incomplete, but in a way Euclid was complete. There's theories that have more or different objects than his, but geometry is considered, and since the Pythagoreans, is kind of the perfect science. Then he gets into Ptolemy. So Ptolemy was about the time of the ancient Greeks, and so it's like a geocentric universe. What the theory was that there's immobile celestial spheres, and so they're concentric celestial, the skies, spheres, that in the terrestrial where we live, then over the earth was like these globes about it. And so the planets were close, and because they spun around the most. And then the farthest stars were fixed, and they never moved. And so between those are the travelers, the wanderers. That the word planet means wanderer, like it wanders across the sky over the course of the time. So Ptolemy came up with the idea of that it's not a flat Earth, and it's not just a moving picture in the sky. It's a great grand design, and we're in the middle of it, and it's in this model of concentric spheres, and then the motions of these are then later in what's called the Copernican revolution. So there's Ptolemy and then Copernicus, because Copernicus is like, actually it's the sun is the center, and we revolve around that. Because then the notions of the epicycles, because the idea is then, well, if it's a circle, it's got to go around in a circle. And so when it comes off and is eccentric in any way, then it's like, well, then these cycles, then epicycles, or within them like loops and these kinds of things. Designing those as a theory to match according to models like constructions or fabricated models of things, why it would be so that they would match up to align with it, so that then the theory of the model can be applied to the theory of this other abstract model, and their conclusions would be the same together or differ as they do. So that was discussed here about Kepler, and so Copernicus is really related with Kepler a lot, and Galileo, and that was the time of Galileo, and it was Galileo was talked about here for a good hour or two back in this moment in motion, and also a bit in this descriptive differential dynamics bit. So Asimov goes on, the rest of this is only a few more paragraphs. He says, mathematicians add to what came previously, but nothing needs to be uprooted. Well, no. Consequently, when we read a book like A History of Mathematics, we get the picture of a mounting structure, ever taller and broader and more beautiful and magnificent, with a foundation, moreover, that is as untainted and as functional now as it was when Thales worked out on the first geometrical theorems nearly 26 centuries ago. Nothing pertaining to humanity becomes us so well as mathematics. There and only there do we touch the human mind at its peak. So this is the quote I read a couple days ago or a couple episodes ago from this. And so now in kind of this slower reading of it, it's to be recognized and understood that here there's a deconstructive account. We're open-minded about the fact that mathematics is through the lens and through the lens and through the lens of those who came before, and and including ourselves in earlier developments, and also ourselves in later developments when we're refined and our lenses are in different directions or something like that. So then as far as that goes, here for this history of mathematics, Asimov has started reading Boyer's book, and he is also affected by the fact that Boyer is basically like, it's the voice from the mountain, is this guy. And so reading this is just like in his style and his tenor of his prose is just it's very respectful of the material. So then begins Boyer's or maybe this is Merzbach's, but one of these guys, the preface to the second edition. It's like, well, yeah, we're coming out with the second edition, got a new revision. This is Uda Merzbach, and he says thanks, and Wiley, and users of this book interested in supplementary exercises are referred to the suggestions in the general bibliography. So Boyer is a historian of mathematics, and so some of the first other footnotes and his references are other historians of mathematics. So he's already, in the first couple chapters, he's already referred to Struick. So Struick is a historian of mathematics, and he's probably most familiar because kind of, from what I understand, and I could be mistaken, that he's most familiar as with regards to something like the Mac Tutor archives of mathematics. So on the internet, there's a place called Mac Tutor, and Tutor, like a tutor, and his name, or Mac Tutor, and so it's and I'm not sure how that's pronounced. And so the idea is that on this, he's collected bibliographies and histories of science. That the MacTutor archives are a great history of science and mathematics, mostly mathematics. And as with regards to the provenance and the authorship and over the timeline of how these kinds of things are developed, is that it's a great perspective over a very good part of the 20th century, at least. So then Boyer also refers to Struve, who's kind of an earlier historian of mathematics. And then in this preface, Boyer is talking about sources and standards. And then there's the origins, then he talks about whether it's numbers or geometry. So Boyer kind of leans in, it's like, well, our fundamental thing is numbers. And here it's kind of like it's geometry. But either way, they're one for the other. So that's numbers, number theory and geometry are each things. And then with regards to the continuous, though, it's kind of the geometry has the continuity first, so that's why it's kind of considered the most usual thing as with regards to these things. And so I'm almost up to chapter 3, and that's about in Mesopotamia, and then there's Ionia and the Pythagoreans. And so that would get into then the great establishment of rationality as what guides mathematics, and that it's kind of a course and it's very particular within it, so that it's rational vis-a-vis its meaning and its import, and for what it is, among other aspects of language and meaning. So I'll be reading this and then trying to extract some works from it. See, here's some calculators. I don't much use my calculators very much. This one, this is like a little Casio. Is it solar? Now, oh, good. I got a screen here from this. Now, the hard part of these solar ones is sometimes they can go, but see, this is a great little calculator. It's got the trigonometric functions. It's got the scientific functions. So we'd call this a scientific calculator. It's called the Fraction, an FX260 Solar. So I got this only like 20 years ago or something like that, but it's kind of cool. I'm happy to have a calculator. When I was a student, this was the only thing allowed, was a non-programmable, non-graphing scientific calculator. But by then, a couple guys had programmable calculators, but they didn't need them, was kind of the idea. Now here, this one, it's lighting up, AC on. This Texas Instruments TI-36. This is in high school. I was lent or given this by one of my instructors, and I never returned it. I was never asked for it back, but I was given this calculator, and it's got some more functions than the Casio we were just looking at. And I'm glad it came on, that the light came on with it. And it's been 30 plus years since I've really employed this very regularly. Perfectly functional. Having the solar powered apparatus is great because most battery technologies eventually disintegrate. This is what's called a TI-36 Pro. Now this I haven't got much into yet, but like a decade or so ago, I was like, well, I want to have some good calculators, so I want to figure this out. So let's see, it's got a solar looking dial on it. I press the button on. Oh, I got a line here. So this is like this is functional. It's giving me a sum. It's giving me a sum. Off. Oh wait, second off. So this is functional, and then as with regards to whether it has like batteries that go in it, say the answer is maybe so, maybe no, but it is solar powered is the idea. Then those are most usually just kind of like a not reverse Polish notation. And so the reverse Polish notation calculator, I wanted to get an RPN calculator because I was less familiar with it. And so this one has got, it needs a battery. So I need to go find some of these watch batteries, you usually call them, to put in here. But what it is it's got a stack machine. Instead of kind of that the operands go apply and accumulate a sum, you make a stack machine, and so it's just a little bit different way that you put the operator kind of plus afterwards. Instead of something plus 10, you'd say 10 plus, and then add the sums and it's on the stack. So I got this particular calculator because I didn't want to get into, because these are pretty heavyweight instruments, meaning it's hundreds and hundreds of dollars and designed to sit on a desk and be functional for many years. This is just kind of a cool thing that I'm going to look to later. I'll go to the local watch guy here and see if he's got some of these batteries of this particular form factor. In case though, really, I'd much use these other calculators, their styles, and this first. Then this other guy right here, this is called an abacus. And so an abacus is construction and is made for calculating. And I saw this, and it's a mechanical device, yet it's really kind of simple. And the way it is it's kind of organized according to positional notation, left to right, say, or in the columns, so that you're able to. There's various ways to compute algorithms. Thus, that by adjusting these ones like 1 through 4, and then the upper one for 5, that by leaving this level, it's possible to quickly tabulate things by walking through different kinds of algorithms on the abacus. And then resetting it is kind of like the Etch-a-Sketch or whatever, and then it just results that this way, that this is, the calculator was at the time that, at least up to some point in time in the 20th century, the fastest calculators in the world used an abacus. And then is to record results on a pencil paper. Vis-a-vis, since the times of like Babbage and computing engines, Leibniz, he implemented like a computer, but the like analog computers like the Antiquity for navigation are ancient computers of whatever sort. And so even larger installations like the Stonehenge or the monuments like the pyramids themselves are in a sense computers. Once a year they compute the time of day. And these are the kinds of things that go into things, but then otherwise these calculators are not so much used these days in my profession, where I'm more at kind of a keyboard in a terminal environment in terms of input and output to computing. But I have spent many hours on the at least on that main calculator, and it's never been wrong. This is I was just kind of going through some stuff here. This is a voltmeter, and so what it has is these probes, and this is a low voltage. This is a 12 volt voltmeter. And so what it's designed to do is when you're dealing with 12-volt circuits, particularly in the automotive, it used to be that anything in the bus of the automotive electrical was 12 volts only. And so it's pretty simple that then thusly the 12 volts DC off the battery, and then that later when the alternator spun up, that would drive like a generator and make current and this and that with regards to then being able to draw off the battery or the 12 volts, is that 12 volts is a very standard voltage compared to the like 120 volts is the usual wall current, and it ranges kind of from 117 to 123. They say it's nominal current, but such a device is part of an auto mechanics toolkit. And it is for thus that because the principle of operation of electricity is that anything that connected conducts does, then it's possible to use this kind of thing to help detect signals and shorts. When you're looking for something that would close an electrical circuit, short circuit, and prevent it from flowing around as wider course is the idea. So we got open circuits are like it's not connected, and short circuits are when it's connected inside the loop. That you want it to go around the loop, and then if it's a short circuit, it won't reach, and if it's an open circuit, nothing does. So these are the kinds of things to figure out. Oh, here's some of these other instruments I was looking at. So this is it's a kind of a micrometer. So this isn't a very expensive micrometer. What it is, it's just a calipers, and so it doesn't really have a micrometer on it. It's a millimeter, and but it enables just to kind of to fix it at a given point with these set screws, and then it's got kind of like an inner. You can measure something on the inside or on the outside, and it doesn't really have a great radius, but it does have kind of like that also for like the automotive parts and these kinds of things that helps reflect that. When you're trying to measure something on the inside or the outside, the application of this calipers and micrometer is kind of the idea. This is a Husky brand, and then it's kind of like so. And it's got these set screws to help kind of identify the fixed points of it as it were. Then this is kind of it's not quite a compass, but it is kind of an angle finder. And so it's got these edges on it and a ruler, and then there's a compass that goes with it. I might not have it here. Oh. But this is kind of just this other piece. This is a very, very similar thing. And what it is just a drawing device to make it so that then when you want to draw something of a particular angle, this will provide an angle. And then the idea of the open angle bit is like this is like a right angle, and then this was like an open angle. And so the idea is kind of like whether or not it's reflexive in a sense, this idea of that angle opening bit. So these are just some examples of tools, devices. These are kinds of things. One other thing that came up the other talk was about the metronome. The metronome is a timekeeping device, usually for musical accompaniment. And then this is a tuning fork, and the principle of operation of a tuning fork has that how it operates is the fork is struck, and according to the composition and shape of the fork itself, it will resonate a particular tone, and then through the foot of the fork, then that tone can be transmitted to resonate through the structure, say. So you start it ringing, and then it transmits the sound through that. Now, perhaps struck it too hard. I mean, but then the idea is that this part of it buffers, otherwise that touching it would obviously apply the plucking of the string or the striking of the string, and is the same kind of principle with these things. Well, all right then, gentle readers. That's what there is for today. A usual course in the history of mathematics and calculators, in a sense. So I so hope you have a great day and a great year, and that in the course of the world's events, that the human condition is a happy place, and then sometimes it gets involved, but it's to kind of remain that way. So good luck, and I shall so hope that next time in Logos 2000 we'll find something that will be as of just kind of a probably more of Boyer's remarkable history of mathematics. So long.